Hello, in this presentation I will tell you about an FPGA platform that we have developed to accelerate DSP and AI applications in wearable computing. One motivation for this work is to accelerate embedded AI applications. Notably, we're interested in human activity recognition from wearable sensor data. Among the techniques that can be used, there exist deep learning techniques, which are well known to be computationally quite heavy, but there are also other pattern recognition techniques such as template matching algorithms. In all cases, we're interested in speeding up computation, and an FPGA platform is an ideal platform to prototype a digital implementation prior to possibly committing to an ASIC translation. Another motivation is in digital signal processing, notably digital communication. There has been a lot of interest in recent years in exploring novel communication techniques in wearable computing, such as capacitive communication or using the body as a capacitive channel. This requires to perform complex modulation and demodulation, which are signal processing hungry algorithms, as well as performing the decoding of the incoming bit stream. And this requires cycle accurate timing, which is something that FPGAs are very good at, unlike microcontrollers. And it also requires to have enough computing power. If we look at the related work, there are a number of FPGA platforms out there. There are commercial platforms as well as platforms from different research groups. We see some highly miniaturized platforms on the top left, as well as more full-fledged platform on the right and on the bottom left. But if we look at all these platforms out there, we realize that there are very small platforms. However, these platforms lack the kind of sensors that we'd like to have for wearable computing applications. Or if they have sensors, they tend to be quite bulky, or maybe they are not available because they are not commercial devices, but academic research projects. In our research group, we have already a wearable sensing platform, which is based on a high-performance ARM Cortex-M4 microcontroller with a wide range of peripherals which are useful for activity recognition research. Notably, we have motion sensor, we have microphone, and we can also extend this platform with additional sensing modalities. The firmware has already been designed to acquire the data from the motion sensor, from the ADC, from the microphones, and all this can be acquired in a manner which is synchronized. So what we're interested in is conserving this platform and notably all the sensors that it includes, and designing an extension that would allow to translate some of the complex algorithms currently running on the processor into a digital implementation running on an FPGA. So we'd like to have an FPGA extension for this particular platform. And this is where Bluemax, the FPGA platform which we developed, comes into play. Bluemax is a 30 by 30 millimeter board with on the top side a number of expansion connectors so that we can stack up additional peripherals. We have a display as well as LEDs, a number of push buttons and status LEDs, and of course the famous reset button. You can see that the circuit is reasonably simple. On the bottom side, we mostly have just the FPGA, an oscillator, and passive components. The FPGA here is an Altera or Intel Max 10 FPGA with 16,000 logic elements, which also includes 18-bit multipliers, PLLs, as well as low-speed ADC. So this platform has been designed to be used either as a standalone platform or as a BlueSense extension. Let's look at the block diagram. At the core of the platform is the FPGA. We have our expansion connectors, and we have the I/O peripherals. Here, the power supply and any additional I/O is meant to occur through the I/O expansion connectors. In order to use this FPGA platform as a standalone platform, we have developed a power supply board. We can connect the FPGA board on this power supply board, and we have an additional USB interface with a UART transceiver, which allows the FPGA to communicate with a USB host over a UART protocol. So we can stack up the FPGA platform on top of base power, or we can stack up the FPGA platform on our BlueSense wearable sensing platform so that we can extend the microcontroller with additional FPGA capabilities. And the resulting system is about 30 by 30 millimeter and 17 millimeter in size, including the battery. In order to characterize this platform, we implemented a linear phase FIR filter. Those are the kind of filters that are commonly used in DSP applications. You can see here a typical implementation of an FIR filter. We implemented that by realizing an FIR filter engine, which reads the data from an input RAM, processes the data, and writes the data to an output RAM. These input and output RAMs are interfaced to the I/O ports. This guarantees that the synthesis tool doesn't do any adverse optimization, and we can really benchmark the amount of resources that are used to implement this filter, as well as the maximum frequency at which this filter can operate. Here, the input RAM and the output RAM are also synthesized within the FPGA. We evaluated the filter on windows of 1024 samples, and we compared two implementations of the FIR filter. First of all, a software FIR filter. This software FIR filter is implemented in C, and it runs either on a synthesized processor on the FPGA. So this is the Nios 2 processor, and we compared both the Nios 2E, which is a compact implementation of the processor, as well as the Nios 2F, which is a high-performance version of this soft-core processor. As a reference, we have also benchmarked the algorithm on our Cortex-M4 platform. The hardware FIR implementation is implemented either using the hardware multipliers available in the FPGA board, or alternatively using canonical sign-digit implementation, which is realized without using hardware multipliers, but using only logic elements. All the power measurements have been done using a power meter supplied by a PC. So we have a 5-volt input, and we verify here the power that is fed through the voltage regulator to the FPGA. So the power that we report here includes the losses of the voltage regulator. So we'll find more detailed characterization on the paper, but we'll highlight a couple of important values. First of all, in terms of power consumption, the hardware implementation uses about 27% power less than the software implementation using the Nios 2F processor. And this is operating at identical clock frequency. But while we have 27% less power consumption, we actually have a 20 to 80 times speed up given by the hardware implementation compared to the software implementation on the Nios 2F processor. So we're much faster and using a little bit less power as well by using the hardware implementation instead of the software implementation. We can notice that the Nios 2E processor is significantly slower than the Nios 2F, and in fact it probably doesn't make sense to use the Nios 2E for this type of application. If we compare the soft-core implementation done using the Nios 2F to the ARM implementation using the Cortex-M4, we notice that the Cortex-M4 is about 15 to 25% faster than the Nios 2F. And this is assuming identical clock frequency. So overall, our results indicate that we have a major performance increase compared to the soft-core implementation as well as power savings. This allows to either reduce further the clock frequency for the hardware implementation and therefore save power further. But we also notice that there is a high static power consumption of about 300 milliwatt, and this is quite significant compared to a hardcore processor such as the ARM Cortex-M4. Let's have a look at this platform in action. So what we'll see here is how to develop and program BlueSense. On the right side, you can see the platform. We program it using a JITAG programmer, and we use the Quartus development tool. Once you power on the device, you'll notice that there is no configuration as indicated by these LEDs. So the first thing that we'll do is open a project and synthesize a design. Here it's a design that is just going to use one of the 7-segment display and show a digit here. Once we configure the system, you'll notice the green LED indicating the JTAG operation, and eventually the device is operational, showing our digit. We will modify this digit, resynthesize the design, and again pay attention to this green LED showing the JTAG operation, and the LED is flashing here, and we see the device being operational. We'll now look at a slightly more complex design, which again we synthesize and configure. One point here to highlight is that so far we have used configuration stored in the RAM memory of the FPGA board. This means that the configuration will be lost after a power cycle. But we can also do the configuration in flash memory, which takes a little bit more time. And once it is in flash memory, it will survive a power cycle. We turn on the device again, and we can see that the device operates. And we'll see here a different self-test circuit. Thank you for listening. You will find this project on my GitHub page. Notably, you will see the schematics, the bill of material, as well as the firmware. You are free to make use of this work or to create derived work, but we would appreciate a citation to this PerCom workshop paper. Thank you.